Hi, everybody. My name is Andrea Del Prete, and I'm from the University of Trento. So the problem I would like to discuss with you today is the problem of controlling a robot manipulator with a discrete time acceleration controller when the robot is subject to bounded disturbances, which we're going to call W. So you can see here the dynamics of the system, which is linear, it's a double integrator, with W entering as an additive disturbance on the joint accelerations. So these disturbances W can be used to model different things, such as sensor noise, modeling errors, or communication delays. And what we really care about in this work is that the joint positions and velocities are always within their limits, which can be hard to ensure because also the joint accelerations are bounded. The tool that we use to solve this problem is the so-called robust viability kernel, which is the set that you can see in this state space plot. So here we have the joint position and velocities on the two axes, and the robust viability kernel is this green set, which contains all the states starting from which it is possible to avoid violating the joint position and velocity limits in the future, even if the system is subject to disturbances. So basically, it encodes the fact that if you are too close to a joint position limit with a too large velocity, like here in this region, you may not be able to stop before hitting the limits because of your bounded deceleration capabilities. So given that the system dynamics we are considering are linear and the disturbances are additive, we can analytically compute the robust viability kernel for this system. And for instance, you can see in this equation the maximum velocity for being robustly viable. So after computing this set, what we need to do is to figure out how to ensure that the state never leaves it. So what we did is to design an algorithm that, given the current state of the system, it computes a range of joint acceleration that ensure two things. First, we want the next state to be robustly viable, so to be within this robust viability kernel. And second, we want the whole continuous time trajectory between the current state and the next state to be feasible. So it means it must satisfy the joint position and velocity bounds. And all of this must be guaranteed even if there are bounded disturbances on the system. So to get an idea of how this algorithm looks like, I've reported here a piece of it, but you're not supposed to read it or understand it right now. I would just like to point out that this algorithm is very efficient because it relies on simple algebraic and logic operations. So you can also use it at very high frequencies, such as 1 kilohertz. So that being said, we tested our approach in simulation with a Baxter robot model, where we have applied always the maximum acceleration computed with our algorithm. And as you can see here in the bottom plot, our method allows the state to never violate the joint limits, despite applying always the worst case disturbance to the system. Instead, in the top plot, you can see that using a classic viability method, which does not account for disturbances, you get a violation of the joint position limit and the joint velocity limit. Recently, we have started working on a more challenging problem, which considers bounded joint torques instead of bounded accelerations, which makes the problem more realistic, but it also makes it much more difficult because it becomes nonlinear. You can find in this paper our latest result on the subject. In the future, we'd like to explore the idea of modeling disturbances as Gaussian random variables, which should result in a less conservative behavior of the system. And with this, I've concluded my presentation, and I'd like to thank you for your attention.